We'll finish up our discussion of 2.2 by defining a vertical asymptote. So remember we discussed the function f of x equals 1 over x. We said that if I have x values that get closer and closer and closer to 0 coming from the right, the denominator of this function is going to get really, really, really small, and the result is that my value will become close to infinity. It'll grow and grow and grow towards infinity. Since my numerator is a positive 1 and my denominator coming from the right must be a positive number, I'll have a positive divided by positive, the result will always be positive, and I approach positive infinity. If, however, I let x approach 0 from the left, I'll still have an expression whose absolute value contains a denominator that gets bigger and bigger and bigger. But since I'm coming from the left, my numerator will be positive 1, my denominator will be negative, and the result of that fraction will grow toward negative infinity. So we define a vertical asymptote. There's a vertical asymptote of a function at x equals a if the limit as x approaches a from the right is either positive or negative infinity, or if the limit as x approaches a from the left is either positive or negative infinity. So you can see here we would say that this function, f of x equals 1 over x, has a vertical asymptote at x equals 0. So this is an example from your notes paper. You'll recall from your work with rational functions in the past that a vertical asymptote happens, it occurs when you have a value that's going to make your denominator of a rational function equal to 0, and there's no way to cancel that factor out with a matching factor in the numerator. So here we've been asked to find the vertical asymptotes of this function. F of x is x squared minus 1 over 2x plus 4. My very first step is to look to see if there's any factoring and canceling I can do. So I factored the numerator and the denominator, you can see here. But there's no canceling I can do. So if I'm looking for a vertical asymptote, I want to check for x values that would make the denominator equal to 0. So I took my denominator and I set it equal to 0. I solved and I got that there is a vertical asymptote for this function at x equals negative 2. Remember, if any of these factors cancel out, that's going to change whether you have a vertical asymptote or not. But here nothing canceled, so watch what happens. So I've discovered that I'm going to have a vertical asymptote at x equals negative 2, and I've been asked to describe how the function behaves to the left and to the right of the vertical asymptote. So in this case, x equals 2. Well, I know for there to be a vertical asymptote, that means the function will have to approach infinity or negative infinity coming from the left and or the right. So I'm going to start by figuring out what this function does as I approach x equals 2 from the right, from numbers that are just a little bit bigger than 2. So I have my factored version of the function here. There we go. I want to pretend I'm going to plug in a number just bigger than 2. I don't want to plug in a number that's far away from 2 because I'll change the values of some of these other factors here. But imagine plugging in 2.1. X minus 1, does that become positive or negative? Well, that would be a positive factor. If I plug in something a little bit bigger than 2 for x, this will also become a positive factor. And I'll have 2 times x is just a little bit bigger than 2, so bigger than 2 plus 2 will also be a positive factor. So I have a positive times a positive divided by 2 times a positive. So I can conclude that my y values are going to be positive. So this is what I've said here. F of x is greater than 0 means the same thing as x. That means the same thing as f of x is positive. Means the same thing as the y values are positive. So I know for values of x that are bigger than 2, as I approach x equals 2 from the right, f of x is going to approach positive infinity. Similarly, if I approach x equals 2 from the left, from smaller values, I will still have a positive value for x minus 1, a positive value for x plus 1, and 2 times, but this time x plus 2 is going to be a little bit less than 0. I'll conclude that f of x must approach negative infinity as I approach 2 from the left.